And another DraftScience video presentation and such. Probably have to break this into pieces, but whatever. I figure we'll start by just playing another physics girl video. Electromagnetic force ought to be worth a laugh. You know, she was supposed to be like a part 2 to this simple harmonic motion, where she was going to be talking about the wave theory, and I thought it would be a connection, but there doesn't seem to be. So electric charge and light is now what this is called too. So anyway, I haven't watched it, so we'll see how that goes. And if it doesn't go that good, then I'll watch the rest of it and then do the video also. But we'll see.
I'm going to bring you in on a little known secret. If you open Band-Aids or little bandage wrappers in the dark, certain Band-Aids glow. I am not making this up. Right at the bottom where the two wrappers meet, as you're pulling them apart, you see a thin glow.
Yeah, X-rays actually. Yeah, so they actually make a device, you know, that uses tape, unrolling sticky tape, to create X-rays to actually do spectral analysis, which is kind of a reach.
Glowing blue line. And it's a really interesting little known type of luminescence, and hopefully by the end of this lesson we're going to understand why it happens. Hello.
I thought you already did a video on this, so you know, just doing another video on this.
Hello, I'm Diana Cowern, and welcome to lesson 18 of Diana's intro physics class. Today is our first lesson on...
Oh, she didn't have the 4 names this time, so at least that's an improvement. So it's an intro physics class, made for, what, 11-year-olds? Pretty much.
Electricity. I am, of course, very excited because we've talked about literally one fundamental force for this entire course. And there are 4 fundamental forces, but we've only discussed gravity. So today, I finally get to talk about the electromagnetic force.
Yeah, so they're all end in the word force, if you'll notice. The weak and the strong are just bullshit. They don't even have an explanation. The strong force is just some magical force that pops into effect. It's so irrational, as an explanation for why protons get close together. So unless, instead of coming up with a real answer, they just accept there's some sort of force that makes it happen. Well, anyway. Electromagnetic. The electro part is sort of irrelevant. It's basically, a magnetic force, but it's basically based on charge. Charge is what makes dipoles and monopoles. And yes, but electricity is something that happens, when electrons are pushed through a wire. But there's no electromagnetic. But anyway, play along.
Today's theme is secrets. Because I'm going to reveal the secret mechanism your car door uses to shock the crap out of your finger. I'm just kidding. It's not a secret. It's in a bazillion textbooks. Did you know that X-rays that show your broken foot at the doctor's office are the exact same phenomenon as the light shining from this flashlight?
No, it really isn't. So you shouldn't have said exact same, because it's really not the exact same.
That's right. Radio waves that carry your radio station signal, the Bluetooth frequencies that your wireless headphones use, they are light. Microwaves that heat your food, light. Infrared heat, light. Red light, light.
Right, except the polarization is insanely different, as is the frequency. And those differences are huge and really can't be accounted for in terms of how we collect the energy. The way we collect it is very different in the circumstance of visible light versus, say, a very long wavelength radio wave, or even infrared.
Light. All of these things are the same thing, and that blew my freaking mind the first time that I learned it. What are they all? They are all electromagnetic waves.
There we go. That's what we were waiting for. We just wanted to hear the wave crap again, So in spite of the fact that they do have these explicit, experiments that show basically that you can quantize or Planckerize the energy in packets. We'll just keep saying this electromagnetic wave nonsense, even though it doesn't fit. And presumably she's going to justify this word wave by using the two-slit analogy, right? And as I've demonstrated, it doesn't work. It's irrational.
It just so happens we can only see a small portion of the spectrum of these electromagnetic waves.
So this is, at least she's did this part right. So at least it goes from radio at the left to gamma rays at the right. I really find it annoying when people put the frickin' high intensity stuff on the left hand side and the weak stuff on the right, because it's just really doesn't make any sense.
So now I know your next question is, you know that a sound wave travels through air. You know.
Okay, so that's a wave though, because we know that's a medium, and if we suck the air out, then the sound doesn't do that anymore. There's no sound anymore. Just can't travel through anything because there's no medium. So until you're ready to say there's a medium in space or there's a medium under the mediums, but you don't have the courage to say that. You don't have the courage to say we're etherists.
So that a seismic wave in an earthquake moves through the ground. So what medium does a light wave travel through? You might say air, but we just established that that's what sound waves travel through. And get this, light can travel through the vacuum of space. If you were a scientist in the 19th...
Duh. I mean, you had to say that. Get this. Surprising fact, starlight travels through empty space. Yeah, the light from the sun, it's traveling through empty space. Wow, isn't that amazing? What were you thinking? It was delivered in bottles or something?
Century, how would you have figured out what medium light moves through?
Yeah, what medium? So, they can't even have the conversation. Again, you can't even have the conversation. We must have dominoes, flipping dominoes. We cannot possibly catapult the domino to the end. No, it can never be understood that way. We must always bang a thing into a thing. We can never, ever, ever imagine that something can just, you get in your car and you can drive down the road. No. Can't work that way.
Knew at the time that all other known waves traveled through some medium, so you assume light should travel through a medium.
No, I never assumed it. I never thought it was a good idea at all. It never made any sense to me. No.
As well. And people are calling that medium the luminiferous ether. And of course...
Okay, yeah, people hundreds of years ago, but nobody's done it in the modern era, so why are what's going to be the game played here? Are you going to own up to the existence of this ether, or are you going to just sit there and do this? Well, we call it a field instead. Field of what? Ether.
They couldn't tell you what it was, but pretty much everyone was convinced that it permeated the entire universe.
Blah, blah, blah. Gotta speed this up a little. I forgot to do that. We'll just go 2.5. Be gentle.
So how could you test for it? How could you test whether this all-present ether existed? If nothing immediately comes to mind, that's okay. It's a pretty legendary experiment that finally settled it. In 1887...
It really doesn't settle anything. That's the whole disappointment here, right? Because this whole length contraction arguments people can use. They can use lots of kind of, the Earth drags a bunch of ether with it, so you can't really do the experiment, blah, 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 blah. And you people don't even know how an interferometer works anyway, so you have no clue. So how can you tell if you're testing with the right instrument when you don't even know how the thing works? You do understand that a half silver mirror is not going to create two equal beams, right? I mean, some of the light's going through little tiny slits, little tiny ones. And the other light's reflecting without going through slits, which means it's not diverging. But you people can't even get that right.
These two guys, named Michelson and Morley, built a contraption...
No, I can't believe they just keep going back to the same old, tired, dead story.
You bounce light waves back and forth this way and then perpendicular this way and see how the light interferes when it comes back. This concept is called...
So the light doesn't interfere. So again, it's another one of these silly things where they don't even get the concepts right. So I'll just do this little piece just because I haven't done it lately. And I suppose I should do a video devoted... Come on. Not that complicated computer. Jeez. So the argument is that you put a beam splitter here, you shoot light through it, okay, one beam reflects, one beam goes through, and you bounce it back, and one beam reflects and one beam goes through, so one beam reflects and goes back, reflects, The other beam reflects over here and goes through. So the point is that the beam splitter, all right, the idea is it's half silvered, so that means there's holes in it, essentially. And the holes just end up being little tiny slits. And so the light that goes through gets spread, fringed, as they might call it. It makes fringes. And the light that reflects doesn't fringe. So the whole path of one beam, okay, no diverging. Okay, the other path, it's diverging through the whole experiment. So when you combine the two beams, what you're doing is you're combining a beam that has been diverging the whole time with a beam that you just started, that wasn't converging, and you just converged at the very end. So you're putting this pattern of rings on top of this pattern of rings. And then you're seeing what kind of equal sign you get, in phase, out of phase. And it's really just about the center. The only part of the pattern Michelson and Morley were looking at is the center, and they were just saying, does it blink on or does it blink off? And that's it. So, it's not as straightforward as they make it all sound to be, like somehow you're measuring distance. No, what you're really measuring is the fact that there's a proportional relationship between distance and how much this light has diverged. And that's what you're really measuring. So again, you've broken a bunch of photons, shooting them through here, you're bouncing them through, and you're seeing how many you're going to put back together again to make your patterns. But, they don't have a clue what they're, actually measuring. Just assume. They just make assumptions. They're very good at assuming things. They're not very good at proving things.
An interferometer, and it lets you compare the path distance one wave goes versus the other. Because when they come back, they interfere. And if, say...
So they don't really interfere. You're just remaking photons again. In phase, out of phase. In phase, out of phase. That's all.
If one wave went further than expected, then something's happening. So the idea was, if Earth is moving through the ether, you would see some change in the speed of light along one direction as it moves through the ether wind. It's kind of like if you're in a car moving along a road that, like, say the road is a conveyor belt, and that would change the speed you're actually traveling in the car. Same concept. Fun fact.
No, the fun fact is think of it as dominoes, and you're going to flip the dominoes, but the dominoes are moving towards you, so now you're going to be hitting the dominoes much faster. So you're going to hit more dominoes.
This is the same technology that LIGO currently uses to detect gravitational waves. But back then...
So that's a fun fact, huh? It's all just fun, Let's not talk about whether the damn thing actually works. No.
For Michelson and Morley, in what was maybe the biggest failed physics experiment
Storytelling.
of all time, they found nothing. There was no measurable difference.
No, that's not true at all. There was a measurable difference. It just wasn't where they thought it should be. That was the weird part about it. There was some measured difference. The difference was just completely not connected in any way to where they expected it to be. It's like they were expecting left, right, they got some up and they got some down.
There was no ether. This was the biggest deal. Because if there was no ether, then what is the medium that light traveled through? The strange answer we know now is that there isn't one.
Ah, yeah, so except for the field that is really ether. The field of ether. So it's just such a pile of crap.
Today we think about light not as a wave traveling in a medium, but rather as, get this, a disturbance in something called the electromagnetic field.
Oh yeah, so that's nothing like a disturbance in the ether. Oh yeah, no, that's nothing like the same thing. Oh no, nothing at all, just like the same thing.
Dude, what on earth is a field? So the electromagnetic field is a type of force field. Yes, it's true, force fields.
Oh, whatever. So again, made of what, doing how, where the energy came from to make this field, the field that's ever present, the dominoes.
They are real. In fact, you're standing in a force field, or I suppose you might be sitting, but you're sitting in a gravitational force field.
Now, you're standing, in energy from the universe, and there's different amounts of it depending on where you're positioned and how close you are to something that might be absorbing energy. If you're sitting on a sponge that's absorbing energy, then there's more energy coming from above you than below you. Yeah, that kind of thing.
I'm going to show you, with some math that you already know, a way to think about what fields...
Oh, annoying. Yuck.
Tonight, I'll be eating a falafel wrap with sweet potato.
Ah, I'm charmed. Yuck.
R. So take Newton's equation for gravity, which you already know, F equals gmm over r squared. Gravitational force between two masses.
Okay, now this is somehow going to get to the electromagnetic field. Okay.
Big M and little m is gmm over r squared. So let's divide both sides by little m. These cancel, and I get F over m equals g.
So that's convenient. Yeah, let's just take one of the m's. There really shouldn't be two m's in the first place because things don't make gravity that way. They both have their own individual gravity, and the total force is kind of a lie because it's the total force of summing how much you are pulling on the earth and how much the earth is pulling on you, so to speak, in terms of how much of a deficit you both create. Now obviously the deficit I create in the field, that is how much I change the energy potential, is very slight, and therefore the earth doesn't move very much. Okay, but the earth is very big, and the change it's making in the space between looking up and looking down, it's making a big difference in the amount of radiation that's coming from one end versus the radiation from the other. And therefore I move into that difference. But the field has to be made of something real, a real force. See, they called them forces earlier, and now they're fields.
M over r squared equals F over m. That's A from F equals ma. So on Earth, this value F over m, or gm over r squared, is little g, or 9.81 meters per second squared. And that's true, but what if we thought about this in a different way? Imagine putting an object some distance away from some planet like Earth. So I'm going to draw Earth. I've got a little object, a distance r away from the center of Earth. So this equation represents the gravitational force per unit mass.
There you
So the
go.
force per unit mass at this point, or this point, or this point, is going to have some magnitude that will be equal to g times m, which is the mass of Earth, or whatever your planet is, divided by your distance away squared. And that force
There you
is
go.
a vector. That's always going to be...
Bravo, exactly. It's a vector. It's a straight line because the force is being used in going in all directions. The Earth is absorbing energy in all directions.
pointing toward the center of the Earth. It's radially symmetric. And as you move further away, the force per unit mass still always points toward the center of the planet.
Right, so it's just like a light bulb except in reverse. Just like a light bulb except in reverse. Well, an old-fashioned light bulb.
The magnitude of the force per unit mass gets smaller. What I've just described is a gravitational field. The field
What you've just described is the inverse square law, which charge obeys, and which magnetism obeys, and lots of things obey. Now, when you get into dipoles, you end up, changing that a little bit, but anyway.
tells me that for a given mass, like little m, in some location at r, what the gravitational force is going to be. It's a vector field, so it has a direction. In this case, every single point will point toward the center of Earth. But if my object is here at some distance away, and say it has a mass of 10 kilograms, I just multiply the value of my field.
Right. So again, she has the arrows pointing in, but the real argument is there's more force on the outside than coming from the point source. The object is radiating less energy than the open space, and therefore the object moves proportional to that distance from the absorber of the energy. The closer you get to it, the more you feel what it's doing.
Field by 10 kilograms, and boom, out comes the force. A field has some value everywhere, and a vector has that, but also a direction everywhere. In physics, we have all sorts of similar vector fields changing throughout space. These fields...
Alright, so again, it's not because some place in space changed, it's because you're throwing less stuff. So like the light bulb, if I dim it, or I turn it down, or I turn it up, I'm changing how much it's throwing out into space. I'm changing how much radiation it's producing. These are fields of radiation. They're not fields of some magical arrow. They're fields of whether there are particles or aren't particles. Is there something with momentum heading for you? And that's the reality. And then they're just so clueless.
also usually have some sort of symmetry, often a radial symmetry like this. And actually, it's not just two-dimensional, it's radially symmetric around a sphere. And you guessed it, the electromagnetic field is one of these radial vector fields, just as...
Now, a charge is. So it's not an electromagnetic field, it's a charge field. And if you put two charges really close together, you have a dipole field. And now the effects will be opposite because electrons and protons are affected by the field inversely. What makes electrons run away makes protons move towards, and vice versa. And that part they'll never explain either.
A mass produces a gravitational field. An electric charge produces an electromagnetic vector field. The electromagnetic field describes the
Now, it's just its charge field, so it doesn't have any electromagnetic. It can't have electromagnetic until it's in a polar environment, until it's with another charge. So again, it is just doing charge.
electromagnetic force per unit charge throughout space. This means we need to talk about electric charges. You probably know that there are two types of charges, where opposite charges attract and like charges repel. And
Right, and that they really, if you want to try to explain that, then you're going to have to figure out that because there's two kinds of matter, a proton and an electron, two oppositely charged matter, that maybe there's two kinds of force, positive force and negative force, and that they affect the objects inversely, and that's why you have an inverse relationship. And that fixes everything, and that explains the strong force. It explains just about everything. Yeah, everything really.
ever since Benjamin Franklin in the 18th century, we call the two types of electric charges positive and negative.
And even though you have them mislabeled, in the sense that if you try to use them to do any kind of electrodynamics, the labels are inverted because the thing you're adding more of is the negative object, which is very inconvenient.
So this will be the field for an electron, which has the opposite charge, so the arrows point in the opposite direction. It is, by the way, completely arbitrary that we call...
So, and again, there is no arrows going in and going out. Because again, from the proton's perspective, the arrows are going out. From the electron's perspective, the arrows are going out. They're reflecting the universe. They can't create a charge. They have to reflect a charge. Just like the Earth can't make energy. All the energy on the Earth, on the surface of it, inside of it, all of it, it had to come from somewhere. It had to be energy that went in before it could be energy going out. And they know this because their own conservation laws basically dictate that this is exactly how energy works. All you do is transfer what object it's in. You just move the energy to a new object. If there's friction, it means you took energy from this thing moving and you put it into the surface, and now it's moving in the surface, and then the energy can come out as radiation and heat a bunny rabbit. I mean, it always is going somewhere. It's always on the move. It's always just converted from being in that chair to that chair to that chair to that. It's always going to a location. It never, ever, ever doesn't have a location. It never dies. It just gets transferred. And that fact ought to tell you that, well, that's how your field works too. Your field has to obey the same rules.
Protons positive and electrons negative. We just do it because that's what Ben did. So we now describe electric charges using the SI unit called the Coulomb. So the charge on the proton, pretty random.
All right, well, I'll take a break here because I do have to take a break, and I'll be back. All right, continuing. I skipped a little tiny bit is, who wants to do this, whatever, redundant, irrelevant almost math. But anyway, she does say something here. It just brings up part of where their physics just doesn't have any continuity.
Charge. It's negative 1.6 times 10 to the minus 19 coulombs. This is so weird. The electron is an elementary particle, meaning that it can't be broken down anymore, whereas the proton is made up of 3 quarks.
See, says you, though. 3 quarks. You'll never explain exactly why I should believe that, what's the great evidence, any of those kind of things. None of those details will be provided. But yeah, it doesn't make much sense. What's clear is that the charge is the same. That is, if you reduce them to a point, something the same size, they're going to radiate the same amount of stuff at a certain distance. But the truth is that maybe they are different sizes, and clearly the mass difference too. Maybe they just don't move as fast. But to start saying what they're made out of, that's sort of dangerous, I think. But you sort of have to make them out of the same stuff for them to be so alike. And the only subtle difference is the protons get stuck in the middle and the electrons end up on the outside, which means the electrons seem to be more capable of moving.
They're two very different objects, but it just so happens they have the same exact charge.
Just so happens. See, do you really believe it just so happens? That it's probably not just a coincidence, that there's some real reason.
So, how many electrons or protons in 1 Coulomb of charge? Turns out you would need 6.3 times 10 to the 18 protons, or 6.3 times 10 to the 18 electrons to get 1 Coulomb. So that gives you some scale. Why so big? Well, because when they were defining the SI units in the late 19th century, they didn't know about protons and electrons. So today we can actually manipulate single protons and single electrons. But back then they were dealing with huge amounts of charge. So now we have to work with coulombs for the same reason that chemists are stuck with moles. What is that, like 10 to the 23? Something like that? Sorry, chemists. We feel you. Solidarity. So Coulomb.
So, yeah, just more evidence of how you don't fix things that are sort of broken.
Of charge. They'll push and pull each other. And we have a tool for calculating how big that force is. Just like Newton's law of gravitation, but for electric charges instead of masses. So our friend, Mr. Charles Augustin de Coulomb, the guy that the electric charge is named after, gave us something called Coulomb's law. So it is F equals K, big Q, little q over R squared. Force between any two charged objects is proportional to their charges, Q and Q, and inversely proportional to the square of their distances, R squared. And with a proportionality.
Right, so it's just the same gravitational principle.
Constant K. K has a value of 9 times 10 to the 9th Newton meters squared per Coulomb squared. This looks a whole lot like Newton's law of gravitation. Yeah, they're both radio fields, but it's interesting that they both are linearly proportional to the charge, or the masses, and inversely proportional to the radius squared.
No, that's not interesting. I mean, it's exactly what you'd expect from something like a light bulb. A light bulb's obeying exactly the same rule. Exactly the same rule. My hand is obeying exactly the same rule. Okay, there's the inverse square law. Here it is, right in your face, so to speak. Half the distance, 4 times bigger. Da-da-da-da-da. So, I mean, it's everywhere, the principle. So, no big surprise that charge obeys the principle.
No. Interesting to me that this looks so much like gravity. Moving on. So, we can use Coulomb's...
So, that's the whole point, right? It's interesting that the forces seem to have all this stuff in common. They tend to do this inverse square law thing. They tend to be moving the same speed. They tend to impart momentum. Gee, why do we think they're different things? No really good reason.
To calculate the force between a proton and an electron. So we'll make the distance appropriately small. Let's put the proton...
So this really isn't getting anywhere near a photon, right? This is really nowhere near one yet.
A nanometer away from the electron. So my radius is going to be 10 to the minus 9 meters away. So this distance is about 20 times further away than the electron and the proton are in the ground state of a hydrogen atom, which is known as the Bohr radius. So the force in this case is going to be my K, so 9 times 10 to the 9th Newton meters squared per Coulomb squared times my two charges. And they're the same magnitude, so I'm just going to square it. And remember to add a negative. So I'll put the negative in front.
Yeah, we'll jump ahead.
So if we compare this electric force to the gravitational force between them, we would get force of gravity is G, which is 6.67 times
Right, so
10.
So this is old obvious stuff. Yes, gravity is a weaker force, but guess what? Charge is making gravity. Every time you move an electron or you move a proton, you're absorbing energy out of the universe. A force is having to push the electron and proton. While it's pushing it, the force can't be making as much progress because it's got to drag the electron or proton. So the force is being diminished for that period of time it's pushing something. It's not actually moving the speed of light anymore. So it's lost, in fact, some energy. And that's what makes gravity. There, simple explanation. You don't need any bent space. We don't need any of the nonsense, blah, 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 blah. So she's just going to tell us something, whatever. I mean, look, gravity's a weak force. Well, gravity's a weak force when you're when you're looking at electrons and protons, because guess what? They don't even care about gravity. They just care about charge. They care about moving each other. That's the field they're in, is the charge field. They're not in a gravitational field, quote unquote, because they're making gravity. Something has to make gravity, right? You do understand this, that there is an effect and there's something that's causing it. The thing that's causing is electrons and protons moving. There isn't any gravity between them because they're charged. They don't care about gravity. They're making gravity by moving. So they can't be affected technically. Well, technically they can be affected by gravity in the sense that something's already making gravity, that is a big pile of earth or something. The electron's going to see the change in the field, so obviously it's going to react to it. But it's not itself making gravity. An electron isn't making gravity when it's standing still. There's no gravity. It's charged. It's electrons in a group that are moving that make gravity. The matter has to move for it to make gravity.
The minus 11 Newton meters squared per kilogram squared.
You're moving right now, right? So just to point it out, right now you're moving in towards the Earth, and what you're feeling is the Earth pushing back. So you're not feeling gravity pushing you down, you're feeling the Earth pushing you back. So you're moving a lot. Every second, parts of you are going up, and then another part of you is going down, and another part of you is going up, and another part is going down. That's how it's happening every single second. These people will never get that simple insight. They will remain in their ignorant little delusions.
Times my mm, my mass of the proton, times the mass of electron, plug these in, times my sign meters, squared. All these calculations, and I get 1.0 times 10 to the minus 49 newtons.
Right.
Woohoo! That is way smaller. That is a tiny gravitational pull. I wanted to point out something on our force calculation.
So let's just understand, there is no gravitational pull between an electron and a proton, or an electron and an electron, or a proton and a proton. They can't make gravity. When they move, they cause gravity outside of their movement. They cause it to the field. They're radiating. More energy goes in than comes out because they're using energy to move.
Notice that we put a negative sign in one of the charges because the electron has a negative charge, which means that the force is negative. So that negative sign.
So again, it's not really any different than it being positive. You could just switch them around and it wouldn't make any difference at all. And it would make things a little more rational, because then when you were adding charges, you would understand that you're adding electrons or subtracting electrons. So at least it would be helpful when you're measuring the total charge of an object if you didn't have to measure it in negative positives. Instead, could have positive positives.
Means that this is an attractive force, which totally makes sense because we know opposite charges.
So more nonsense, an attractive force. This is mushy language, because you know the same force makes an electron go one way and makes the proton go the opposite way. So let's not talk about, there's no one of them does in and one of them does out. No such thing exists. That's just absolute nonsense.
Attract. If we had done the same calculation but the charges were identical, like two protons, then the electric force would be the exact same magnitude, but it would be positive, meaning that it would be a repulsive force. This is the big difference between the electromagnetic force and gravity. Gravity is always attractive.
Because gravity is the actual consumption of a force, where charge is the creation of movement between electrons and protons. Gravity is the consequence of the movement.
Under normal circumstances. Whereas the electromagnetic force can be positive or negative, so it can be attractive or repulsive. I said.
So again, there's no point. You're attractive, repulsive. You're either creating something in the field, or you're not creating something in the field. And obviously, you have to go a step further and understand that there's two forces that complement the two charges, and that's why there's an inverse relationship, because the electron force doesn't affect a proton, and the proton force doesn't affect an electron in terms of making it move. It just converts the force, changes its direction. And obviously their like forces reflect. Everything can do in the universe, matter just reflects the universe that hits it. And how it reflects it is how everything is explained. Nothing's created. It can just bounce off. Energy just bounces off of matter.
Under normal circumstances for gravity always being attractive, because there's actually some hypothetical situations in which you get a repulsive form of gravity in the early universe.
So they just making this crap up.
This theorized period of time where the universe expanded at this insane rate of expansion called cosmic inflation.
Yeah, they had to just make it up because their theory didn't work. And so they just said, well, because it's not moving fast enough, we'll pretend it went light speed. So you have a plane and it's not going to get to California on time. So you just pretend, well, for 5 minutes it went light speed. Who cares? We're just making that up. But that's all they did.
The period of time was called. And it's theorized that this inflation was caused by a repulsive form of gravity.
That just showed up to do this one thing for you, just to fix your math. Just like the dark energy magician showed up to fix your gravitational errors in your math, some more wrong predictions. So that's all they do, right? They say, oh, we have the most predictive theory in the history of mankind. Yeah, because they just keep inventing bullshit to fix all the errors.
We can apply all these ideas to talk about the electromagnetic fields generated by charged objects. So if I asked you now to tell me about some electromagnetic fields, you could do it, right? And by tell me, I mean describe them using math. No? Okay, I'll help you. But first, let me show you a fun little demo to get us in the mood. So when you weren't looking, I stuck some tape here on the wall of our Magic Science Space Bus 3000. And I'm going to pull it off. Blah. Okay, you can do this too by sticking tape to the walls of your space bus or to some plastic. Once you rip the tape off of the plastic, they will repel each other. Ooh, I don't know if you can see that, but I'm trying to make the bottom touch, and it will not. So what I did was make an electromagnetic field on this tape, and it's repelling the charges on this tape, and vice versa. Field on this tape, and it's repelling.
Right, and because there's real things, and they're called electrons, and they know that. Okay, so what you did is you pulled electrons off the wall, and now you have an extra amount of electrons on the surface and an extra amount of electrons on the other surface because you pulled them off the same wall. And so the electrons are repelling each other. The end.
The charges on this tape. That's pretty cool. But this is pretty hard to model. So what about modeling the electromagnetic field of a proton? Just like
so the inverse would be is you pulled the electrons off, okay, you left them on the surface, and now more proton is showing because you remove some electrons. That means the nucleus is now more visible. So the plus can now be seen because you don't have to shoot it through a bunch of electrons. And so now the positives are reflecting off the positives. But they won't go into any of those details because they don't have an explanation. All they can say to you is virtual photon force carrier or something. They'll say a messenger goes from one piece of tape to the other piece of tape and says, well, depending on whether you're plus or minus, you go that way or you go that way. Okay? So depending on what I'm just here to tell you this is how it works. If you're plus, you go that way. If you're minus, you go that way. Okay? There's no real mechanism. There's some storyteller photon, right? So some photon flies up there to tell them which way they're supposed to go. They have no mechanism. There's no energy. They can't follow the energy. They can't because they don't even know where it came from. Because they don't understand that the only thing something can produce is what it has previously absorbed. And now it can produce it because it absorbed it. But you have to absorb it before you can produce it. And the rest of what you're producing is just reflections.
With gravity above, where we divide it out by the little m, we're going to start with Coulomb's law, which you now know is F equals K Q Q over R squared. And we're going to divide both sides by Q to get the force per unit charge. So we're going to get F over the little q. This is like my unit charge, and I'm going to get K big Q over R squared. This is my electric field for the proton. It looks like the one we drew before, but the field is going to be repulsive by default, which is the opposite of gravity, which is attractive by default. So if I put another positively charged object in this field, it will feel a force radially away from the proton. The further away I move that charge from the proton, the smaller the force gets by 1 over the radius squared. So if I put a negative charge in here, the sign of the force is going to flip, and that charge feels an attractive force. This is what we mean.
You already did that part, so yeah, do it again. Great, thank you.
By the electromagnetic field. More specifically, this is...
No, so there's no... This is what we mean by the field, that it's just magical numbers in space, and it doesn't represent anything mechanical happening in the space.
Is the electric field. We haven't included any magnetism yet. But the electric field tells us how much force a charge would feel at a particular location, R. Twice as much charge in there, so you increase Q, and you get twice as much force. So if we want to be fancy, the electric field is a vector representation of the force per charge that a charge would feel when put near another charge.
Right, so it's just how much light from what distance. So again, it's the same principle as a light bulb. And if I made the light bulbs blue and red, okay, for proton and electron, and I made a simple rule that when, blue light hits a red light bulb, it turns 90 degrees. and the light bulb stays where it is, and vice versa. And they made the simple rule that the red reflects off the red. So if I'm a red bulb and that's a red bulb shining, my light bounces off of him and bounces right back to me again. So I'm automatically going to be repulsive based on how close I am. The closer I get, the more repulsive it's going to be, because I'm going to be doubling the amount of impacts that happen. So I go half the distance, I'm going to double the amount of times this stuff is going to be hitting back and forth.
Got it? Great. So besides a single proton, another classic example of an electric field is actually quite close to the tape demo that we did, because it involves two conducting plates where charges can accumulate. All
right, so this will be another joke. Well, let's see. I hope she's not going to do the cashmere thing, because they never get that right.
Actually what I did with the tape. When I ripped it off the plastic, I actually ripped electrons off the wall, and the tape became negatively charged. So then the negative charges on both strips of tape repelled each other. Which reminds me of an excellent joke. So one atom says to another, "I've lost an electron." And the second atom says, "Are you sure?" The first atom replies, "I'm positive." Okay, so two conducting plates, some distance apart. They could be two sheets of tinfoil or two metal sheets. So these are real objects. You could really do this. So we attach a battery to these two sheets.
So again, this still has absolutely nothing to do with the original, what she was implying she was going to get to, which is this electromagnetic wave that we call photon. So electric charge and light, there's no light in this so far.
One end to the positive side of the battery and one end to the negative side, then what's going to happen? Well, on the negative side, a lot of electrons are going to pile up on the sheet, and so you're going to get a bunch of negative charges. And on the positive side, the electrons are going to leave behind some lonely protons. So we're going to get a bunch of lonely protons, giving an imbalance of charge, more negative over here, more positive over here. So now we have an imbalance of charge with electrons on one side, protons on the other. And each proton is going to have an electric field radiating out like this. And each electron, because
each red bulb is going to be emitting red light, and each blue bulb is going to be emitting blue light. And depending on where the blue bulbs are, right? If there's a red light in front of the blue bulb, you're not gonna see much of the blue bulb, right? Right? But if there's no electron, then you'll see the red bulb or the blue bulb behind it. You know, that's all there is. And if I move this quickly, you could say, "Oh, it all looks purple to me." Yeah.
this negative is going to have the same kind of field, but opposite, where it's going inward towards the charges. So what ends up happening is that all of the sideways pointing fields cancel, and so you end up getting this field that's actually all in one direction. And
so it doesn't have a direction. They're both producing a reflection of the universe. So the red bulb's reflecting red. The blue side is reflecting blue. There's no direction. The direction just comes from the fact that if I want to do something in terms of inducing a current in a wire, then it becomes relevant which side is positive and which side is negative, because there's a right-hand rule. So when I'm turning the force, it turns in one direction. But it has nothing to do with there being actually something moving in that field. There's nothing going through that field. There's blue light coming from one side and red light coming from the other. That's all that's happening.
now, where in here do you think the field is the strongest? Say A, B, or C? It is a trick question. They are all...
Yeah, it is a stupid question. But regardless, if you're trapped in a infinite plane circumstance, that is, unless she goes right near the edge, they're going to be equal. But the fact is, yeah, if it's not an infinite plane, if it's not a very large surface and you're just measuring one tiny part on the surface, you can sort of understand that at the edges is where you can get lots of energy from other places besides what the light bulb is showing you. The other side is showing you.
all the same strength electric field. Except at the edges over here where the plates end, you get
Okay, well, at least she's conceding the point.
a constant electric field between the two charged plates. Typically when you do this kind of electrically charged plate problems, you have plates that are a lot longer than the distance between them, so you can ignore the edges. So no matter where you put another charge in between the two plates, it's going to feel the exact same force. If you get...
You can't evade the light because it's actually reflecting constantly. So you can't be in a position where there's less of it. And the same is true for gravity, right? You know, you can make this hollow sphere argument. You create a hollow sphere, and at every point there's no gravity because you're exposed to more light, right, from the distance. The far away light, you get more of it, but it's further away. But the other side is giving you a lot more intensity, but there's less of it. You know, so the two equal out. So you always end up with nothing as a difference.
Further away from the protons, well, you get closer to the electrons. So the protons are pushing if you're a positive charge, and the electrons are attracting or pulling if you're a positive charge. So it all balances out. So you get this constant
Right. So, but there's nothing like that happening. There's nothing like electrons are pushing across this field or there's something moving in a direction. It's just not happening.
electric field in here, all going this direction, which means that if I throw an electron in here, it'll go that way. If I throw a proton in here, it's going to go that way. So this setup is actually something you probably have hundreds of in your pocket right now.
Right, so that would be a giveaway that this stream can't be flowing in one direction, right? Because then the proton has to fly against the stream. It doesn't make any sense. So there can't be a stream going in one direction.
Now, it's a super common electronics component called a capacitor. And it's one of the fundamental electrical components of modern electrical technology. So your phone very likely has hundreds of them, along with resistors and transistors. So let's stick a little electron in here and see what happens. Well, it's going to be pushed as we established before, which means that it won't just move, it's going to accelerate because it feels a constant force. So say we measure the force on that electron, which would be really hard to do. I don't know. Maybe you can think about an experimental setup to figure out the force.
Yeah, well now she'll probably make the mistake of using the silly 1/2 mv squared to measure its energy. Yeah, you're not going to get the right answer with that wrong formula.
The force on the electron. But say we measure and we know that the force on the electron is 7.0 times 10 to the minus 14 newtons. So from that, we can figure out the electric field strength inside this capacitor. So what is it? What's the electric field strength? Well, before we did the radial electric field, F over Q equals KQ over R squared. But
well, then you have to do the distance and all this. It's not really, it's kind of an air capacitor.
This isn't radial anymore. This is a constant linear electric field. But I can use the same concept. F over Q equals my electric field. I'm just going to call it E. And this is another model. E, this electric field, can be any type of field. It can be radial. We could just have it be a constant, and that means it's linear. It could be all types of crazy geometries. But right now, it's constant. So to find E, I'm just going to divide the force, 7.0 times 10 to the minus 14 newtons, by my charge. And what charge am I going to use? I'm going to use the charge of the electron, because that's what I put in there.
But there is no consistency. So again, this is another defect. All I have to do is put a little dimple on this, or a little bump in it, or a dent in it, and all of a sudden the E isn't the same everywhere. Blah, 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 blah. But whatever.
An electron. And you know that the charge of the electron is negative 1.6 times 10 to the minus 19 coulombs. I get negative 4.4 times 10 to the 5 newtons per coulomb. And the units of the electric field, or you can use volts per meter. Whole new unit now, the volt. Something we're going to get to a little bit more next lesson. So about 4.4 times 10 to the minus 5 newtons per coulomb. What strength does that correspond to? Well, if it were about 10 times stronger, then it would be a strong enough electric field that you would actually get a spark through the air if this were sitting in the air. Typically, we think of these capacitors as being in a vacuum because air actually affects the electric field. But imagine I had an electric field that strong across air. The electrons would be pulled so strongly toward the positive side, they would jump across the air. And that's actually what happens with the Band-Aid that I talked about at the very beginning of all this.
Okay, so that had something to do with the light you see. And again, which are a proportion of them are X-rays, actually. They're obviously violet and, higher. So it's actually producing X-rays.
When you're pulling apart those pieces, you create such a big charge imbalance. Positive charges building up on one side, negative charges building up on the other side. Such a strong charge imbalance that electrons jump across through the air. And when that happens, you see a spark. That's what a spark is. So now we understand why Band-Aids glow. Maybe not all of it, but enough. So that's the electric field. I know that we didn't talk much about magnetic fields, but they are...
Yeah, you didn't talk about anything, in a coherent manner. So yes, you jumped from one thing to the other and didn't really get to anything like what caused the photon, how did the photon get made, why do we see the electrons jumping across?
Very closely related, and we didn't get a chance here to go in depth, but they're two sides of the same...
And what did they have to do to be able to jump across? So again, if it was a vacuum, they wouldn't be doing that. They wouldn't be jumping.
Fundamental force coin. And in fact, there are great resources out there that I suggest you search for that teach you how the magnetic field is actually the electric field kind of in a different reference frame. I didn't learn any of that until I got to relativity.
Oh, brother, a different reference frame. Charge creates poles, and then you can make dipoles out of poles. You put charges together, you make a dipole.
College.
That's a magnet.
Anyway, we started this video talking about electromagnetic waves. So how do you create waves in the electromagnetic field? Well, this animation shows you how. What we have here is a radio station on one side, so basically an antenna, and then some distance away you have a house with another radio antenna. What happens is the radio station is basically just jiggling electrons up and down in a metal wire, so it's an alternating current, if you will.
All right, so that's the funny part, right? That this is what they actually are trying to sell you. So the polarization, again, is thousands of atoms. The thousands of atoms in the height of the wave. There has to be. That's its polarization. It's huge. Thousands of atoms worth. So some single electron goes jiggly, jiggly, and makes something thousands of atoms. Obviously, it doesn't happen this way. So they just made this up. It's not even close to the truth. It can be debunked as just something they made up. It's just nonsense. That's not how it happens. They don't even have an explanation for how the electron is being jistled this way or jistled this way. They don't explain how it does that. How does it do that? How does it move? What's moving it? What's moving the electron? The magical electrical moving of electron thing. Okay? But no explanation. But I didn't think it would be this bad. I mean, this is just absolutely silly.
So you can see when the electron jiggles, the electric field changes. So sometime later, the electron in the other antenna, that one also starts to jiggle.
So just an amazingly simplistic, nonsensical pile of mush that has nothing to do with the experimental evidence that any electron communicates with another electron with a photon. Because it really can't happen that way. It can't.
Why? Because it's feeling the...
there's reasons why photons are only created under certain circumstances, and you can only receive them under certain circumstances. You can't see them anyway. You have to see them by creating electricity. Even a photomultiplier requires that. And it's the polarization of the light is integral. It's fundamental to creating the electricity, because it's basically telling you it's got to hit something more than once to cause enough motion in another electron to cause it to become an instigator of an electrical current.
The force field changed. The electrons are responding to that change in the electric field. And if you watch the amplitude of the electromagnetic field carefully, you see that the electric field is oscillating like a wave through...
So again, there's no possibility, because that oscillation has to be thousands of atoms in height. So again, a single electron wobbling cannot be creating the wave. Not the electrical portion, certainly.
Space. And you can see the electron in the antenna responding to that oscillating electric field. There it is. This is the electromagnetic wave that we spent this entire video building.
Oh, so amazingly simplistic, underdeveloped, mush, just a terrible... but this is what it goes back to. They just have these silly notions of reality. They're not really connected to the experimental evidence, and they just sell people this baby talk, and it's just mush.
That wave is light. And that, my friends, is today's lesson on electromagnetism. When they ask what you learned on YouTube today... So
there is no wave. The two-slit experiment's a big fake and fraud, okay? It's a big phony. And there's just no reason to believe light's a wave. It's clumps of momentum. And the momentum basically has to tip an electron. That is, it has to hit something more than once for the event of electricity to happen. There has to be more than one event.
Here are your two key takeaways. Number one, the electromagnetic force between two objects is proportional to their charges and inversely proportional to the square of the distance between them.
A light bulb and everything else obeys the inverse square law, yes. Lots of inverse square laws all over the place.
F equals KQQ over R squared. And number two, light is a wave in the electromagnetic field. And light carries...
No, it isn't. They just say it. They really haven't proven it. And the evidence is, in my opinion, almost completely against it. Okay, all of the good experiments, okay, black bodies and the photoelectric effect demonstrate it doesn't make any sense as a wave. Richard Feynman said it didn't work that way. It ain't a wave. And they still just keep saying it. It's a wave, it's a wave, it's a wave.
Is the information that charges have accelerated. And don't forget to go practice these problems. Here are all the problems.
So again, charges accelerating is just more mush. That has to do with atoms changing their shape, which means they become polar. When an atom changes its shape, you can understand its polarity changes, right? Just like I pointed out, if an electron's here as an atom, I'm going to look negative to you, right? But if the electrons are over here as an atom, I'm going to look positive to you, right, if I'm the proton. You can sort of get that it's kind of nonsense to sit there and say, oh, the atom is neutral. No, it's not really neutral. It's neutral if you take an overall view of everything at once and then look at it and say, it's purple. But the fact is, at certain perspectives, it's going to be red or it's going to be blue.
As we did in today's lesson. Go to them on your own because that is the best way to learn physics. Actually, to learn most things. And now here's something super cool. Something related to light and Einstein and relativity, which I talked about. Early experiments about the nature of light also led to two other really famous insights from Einstein in 1905, which was that the failure of physicists to find any evidence for the ether gave credence to the mind-bending idea of special relativity.
Oh, no, what it gave relevance also to was his mind-bending idea that maybe Maxwell's equations shouldn't be interpreted as wave equations because they're really quanta equations. They really are straight line vectors, and it really is a force, that has a quantity in it. Okay, it's not a field of some mush; it's an actual substance. That was his paper on the photoelectric effect, where he actually, he conceded that, this has served us very well, this wave mechanics, but it doesn't really work, is what he says in the paper pretty clearly. It doesn't work. So it's time to move on. That's what he's saying in the paper. So you ignored that paper, though.
Crazy kinds of physics. At the same time, Einstein proposed the idea that light is not just a wave disturbing the electromagnetic field. It can also be seen as a particle called the photon, which I mentioned earlier. And now we know that all sorts of...
Yeah, whatever. Photon's a really stupid word because it's a composite object at any rate. It's more than one event. Photons don't just arrive and say, I'm a photon, I just arrived, all of me arrived at once. No, photons happen over a period of time. A photon is an event. You haven't even got that clue yet.
Fields are associated with particles, like the Higgs boson, which is a particle associated with the Higgs.
So, just keep... Well, we also have our other fables. We have a talking goose, and we have a talking fish, and, we have magical wizard, and, we have, all you have is a bunch of little baby silly stories that don't have any mechanics in them. They don't have anything to do with physics. They're not physical, mechanical things. They're all just magical things. The magical dark energy and the black forces and the black hole and the what's it called, dark matter. Silly. Oh, light is bent twice as much by gravity. Yeah. Even though it's massless, twice as much.
Field, and was one of the biggest discoveries of the century.
Piece of crap. All just crap. Okay, immature babblings. Okay, really underdeveloped theory. You might as well be telling me that giraffes get longer necks because they want to have a longer neck. And their kids inherit their desires. Now, yeah, you could make that argument, but it's stupid. And that's what your physics is. Your physics is in the same stupid mindset. You just keep looking for silly answers.
In 2012. Or the yet undiscovered graviton, the particle associated with the gravitational field. We've never confirmed that the graviton exists because we can't measure it since the gravitational field is so weak.
Which is also silly. The gravitational field is so weak. You're pretty stuck to the Earth, aren't you? It's so weak that you have to use giant hydrogen bombs to get rockets off the ground. Because it's so weak. Yeah. Okay. Sure.
But you never know. Maybe someone who builds an interferometer the size of the solar system will do it. It could.
So again, you don't even know how an interferometer works. Explain to me again how the beam splitter creates two equal beams by sending light through little tiny slits. It's a bunch of little slits. It's what a half-silvered mirror is. Understand it. It's a bunch of little tiny slits. And they already know that little tiny slits make light spread. So how can the two beams be equal? It's just not possible.
Be you. And if you continue on with physics, which I certainly hope you do, you could study physics like that. And now for a message for you.
You should understand that there's bullshit in the world, and it gets financed for some dopey reason. People like religion, they finance it, they put money in the cup. Yes, propagandize, tell other people, try to brainwash children. Yes, keep everybody believing in the nonsense. Ugh, it's just horrible.
From a special guest. Hi, I'm Vanessa from
Oh, who cares? I'm sure I hate you.
the YouTube channel Braincraft. And
Oh, behavioral scientist. Oh, no, that's got to be just too good, right? Yeah, they know how to do everything right. Yes.
this is a message for all of the beautiful physics nerds who are watching Diana's Intro to AP Physics course. I've learned a lot. I hope you are learning a lot. And I have one more thing to share with you, which is that I actually studied science at university. It was super fun, and it has led to all kinds of...
Super fun. Yeah. No, it is kind of silly, though, because it really... I mean, learning is difficult, especially when concepts aren't clear, and you have to mix unconnected things and then try to make them coherent. It's very frustrating. It's putting together puzzles that are like 100 years old, and like a rat ate a bunch of the pieces, and they're all moldy and bent crooked and all kinds of shit like that. And it's really frustrating to try to put it right.
unimaginably cool things that I have done in my life since I graduated. I have taught astronomy in Papua New Guinea and all around Australia. I actually worked as an astronomy tours manager.
Well, that doesn't make much sense that you're supposed to be some sort of behavioral something or other. Yeah, okay, that makes sense. Why not?
So as a science tour guide in the tourism industry, and every night I got paid to look up at a blanket of stars in the Australian outback night sky, use all kinds of big telescopes and show planets and deep sky nebulae and all kinds of cosmic phenomena to the guests that were staying at this.
Yeah, some retards. So you just propagandized the silly religion to a bunch of gullible dupes, and they ate it up and blah, 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 and you all had whatever, s'mores and roasted some marshmallows and blah, 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 blah.
It was super cool, and it goes to show that there are all kinds of jobs that you can't even imagine instead. I did that, I've done a bunch of other things, and now I am a YouTuber. So there you go.
Oh, yeah, there you go. And I need subscribers. And it was really nice of whatever her name is, Diana, to let me whore on her channel, because that's all it's about. We all have to whore for each other so we can make each other seem significant and important, because that's the way to do things. That's the way to do things right. I learned that in behavioral school. Whoring and lying and shystering, it's fundamental to human function. I mean, you just can't ever tell the goddamn truth. I'm just whoring for attention. I would like you to go to my channel. We're not smart enough to put a link to it in the video, but yeah, go to my channel. Silly person online. It's my name.
Hope you have learned a lot from everything, because you know what? Learning is fun. I love it.
Oh, blah, blah, blah. It's too bad you're not learning anything that's like accurate and factual and truthful and honest. Instead, you're learning babble and bibble and nonsense, a little human glorifying crapola. You're a fish, okay? A silly fish in a striped shirt. Yeah, that's what you are. Yeah, okay, you got thicker skin than a fish. You're a little more... Well, they have scales and everything. Yeah, it's just the gill thing, right? Without the gill thing, they do just fine, if they had the lung thing. Well, I guess they would dry up. Regardless, you're just a fish. Your skin is even made of scales still. I mean, we're fish. And you're just being silly. You have this big giant brain, right? We're big-brained fish, and all you're doing is still doing little fish things. You're not doing anything big and mature and grown up. You're still just behaving like fish.
And I love you too.
Oh, I love
Good
you
and Gather
too.
has no high fructose corn syrup, no artificial sweeteners.
Endeavor to persevere, Gary. So, lead writer... Joe Smuck, Stupid Fuck, William Fucktard. Anyway, so she didn't have a sponsor this week. Oh, no sponsor. She's only got 3,150 views. Yeah, sorry, I'm enjoying that a little. She basically told PBS to shove it. And, she's paying for it now. Anyway. But she shouldn't be supported by anybody. Frankly, it's just mush. Mush, mush, much. All right, so it's just all the usual bibble from the comment sections. You know. Love you. Oh, you're so good. Oh, I learned so much. Oh. Idiots. Fucking idiots. All right, what am I looking for? Yeah. Yeah, I'll do this. All right, so anyway, so this has been a DraftScience video presentation. See you next time and such.